At this point, we're going to pick up the pace quite a bit and fit several examples into the video, because now we've laid the foundation of what each of these problems means or what they each represent, and now we're moving into how to actually calculate these problems. Problem number 4 asks us to evaluate this integral 6 dx equals 7 to x equals 4. I'm going to start by noticing that this is the same as the opposite of the integral of 6 dx when x equals, going from x equals 7. So it's the opposite of what I'd get if these. You don't have to do that, but I wanted to show this so that you could see the problem written as an area problem also. But notice that this, the summation from x equals 7 to x equals 4 of, or the integral from x equals 7 to x equals 4 of 6 dx is the same as the opposite of the integral from x equals 4 to x equals 7. So when I reverse the indices, it just changes to its opposite. So if I'm looking now at this problem, integrate 6 dx from x equals 4 to x equals 7, it becomes an easy problem geometrically, because all we've got is y equals 6, or in other words, this horizontal line whose height is 6 units tall, from 4 to 7. Now if you counted from 4 to 7, you'd see that this length is units long, and if we're going up to y equals 6, you see the height is 6 units tall, so we're getting an 18 for the area if we just used a simple grade rectangle. But you don't want to stop there and say, okay, so I've got the answer. What you need to do is make sure you can do the calculus here. And I'm going to bring in a special guest, Yoda, to help us with this. Here, let's have this standing over here to the side. Here, we're going to bring in the special guest, Yoda, to make sure I don't make any other mistakes. As you see, I already made one mistake and scribbled that out. But look at this integral from x equals 4 to x equals 7. We'd have the opposite of 6 times x to the 1 over 1, or in other words, just 6x, from x equals 4 to 7. So we're going to start by letting x equal 7, and then subtract from that what we get when x equals 4. When x equals 7, 6 times 7, when x equals 6 times 4, so we simply get 42 minus 24 is 18. And then don't lose this opposite that we had out here. To also do this problem in reverse opposite, you see that if we had not switched the order, we would have had 6 times 4 minus 6 times 7. So we would have had 24 minus 42, which would have still given us the negative 18. So there's not some reason that we have to change this to the opposite. The only reason I changed it to the opposite, you could see this area problem also. Let's go on to problem number 5. Number 5 asks us to evaluate the integral from x equals 0 to x equals 4, 9x squared plus x minus 4 over dx. So I'm going to integrate the 9x squared is 9x to the 2 plus 1, so that's 3 over 3, plus x to the 1 plus 1 is 2 over 2, minus 4x 0 plus 1. You have to remember that it's as if there's an implied x to the 0 here. And x to the 0 is just 1, so that's why we see it. But x to the 0 plus 1 would be 1 over 1. If you need a reminder, a mnemonic, a way to remember that when you do the derivative, you decrease the exponent. When you do the integration, we increase the exponent. One way to think of it is integrating was a step after or a step up from deriving. So when we integrate, what we're going to do is step up the exponent rather than step it down. We go back to derivatives, it's a step back, a step down, so we would go x to the 2. Next, what we're going to equal 4, and then let x equal 0. Plugging that in, we then subtract, and here's that calculation worked out. If you need to, you could pause the video to verify that you're getting the same result, but there it is worked out. Let's look at number 6. In the same way, if we integrate 2x times x minus 5 over dx, the only additional step here is that we're going to want to simplify this 2x times x minus 5 to get, or in other words, distribute it. 2x times x is 2x squared, 2x times negative 5, negative 10x. Integrating, we get 2x cubed over 3 minus 10x squared over 2. Let x equal 3. Let x equal, and subtract them, 27. Number 6, oh, that's 5, 8, 6 both. So number 7 is done in the same way. Number 7, it's just that when we see this radical, we simply remember an x to the 1/2. So when we simplify this, we'd say let's integrate from x equals 4 to x equals 0 to x equals 4, 2x squared plus x to the 1/2 dx. So we'd get 2x cubed or 3 plus x to the 3/2 over 3/2. And by the way, when we do that, x to the 3/2 over 3/2 is x to the 3/2 over 3 times, because dividing by 3 over 2 is the same as multiplying by 2 over 3. But once we do this, if we substitute in letting x equal 0 and subtract that from what we get when x equals 4, a difference of 48. Number 8, we're going to use the fact that the derivative of a tangent is secant squared. So the integral of a secant squared is going to be tangent of x. So the integral of secant squared is tangent x. 6 times secant squared would be 6 times tangent x. And then we let x equal pi over 3, let x equal 0. Using the unit circle, we can calculate out that tangent of pi over 3 is the square root of 3. Tangent of 0 is 0, so we get a 6 square root of 3. And then lastly, in video number 9, let me move these so we don't see the back, and we've still got Yoda here helping us. Number 9, it's just a matter of simplifying this before we integrate. So to simplify this, if there's a single term in the denominator, we can divide each of the numerator pieces by the denominator. So we could rewrite this as y over y to the 5th minus 5y cubed over y to the 5th. 6 minus 5 is 1, so we just get y to the 6 over y to the 5 equals y to the 6 minus 5, or 1, minus 5 times the 3 minus 5 is negative 2. And if we integrate that and substitute in our negative 5 and our negative 1, you should get an end difference, an end result of negative 16. I hope that this full as you work through the review problems of number 9.